Hello, my name is Marissa Hernandez, and I am majoring in electrical engineering. And then for this PowerPoint, I will be discussing how to model a DC motor. A DC current, or a DC motor, is an electrical machine that converts electrical energy into mechanical energy. The DC motor is based on the principle of when a current-carrying conductor is placed in a magnetic field. It will experience torque and have a tendency to move. This is essentially known as motive force. Reversing the direction of the current in the wire will also cause the direction of a rotation to reverse. The interaction between the mechanical and electrical fields uses a mechanical force, which will essentially establish the working principle of a DC motor. The DC motor was a suggested topic because it is widely used in control system applications. You can find some DC motors in cranes, air compressors, vacuum cleaner, sewing machine, and many other products that we use daily. There are two electrical elements of a DC motor: the field windings and the armature. The armature windings are made up of current-carrying conductors that terminate at a commutator. DC voltage is applied to the armature windings through carbon brushes which ride on the commutator. There are four different types of DC motors. There's the permanent magnet, magnets connected in series, shunt, and compound. The permanent magnet motor uses a magnet to supply field flux. Permanent magnet DC motors have excellent starting torque capability with good speed regulation. A disadvantage of permanent magnet DC motors is that they are limited to the amount of load they can drive. These motors can be found on low horsepower application. Another disadvantage is that the torque is usually limited to 150% of rated torque to prevent demagnetization of the permanent magnets. In a series DC motor, the field is connected in series with the armature. The series motors develops a large amount of starting torque. However, speed varies widely between no load and full load. Series motors cannot be used when a constant speed is required under variations of loads. Also, the speed of a series motor with no load increases to the point where the motor can become damaged. Some load must always be connected to a series connected motor. In a shunt motor, the field is connected in parallel with the armature windings. The shunt-connected motor offers a good speed regulation. This field winding can be separately excited or connected to the same source as the armature. An advantage to a separately excited shunt field is the ability of a variable speed drive to provide independent control of the armature and field. The shunt-connected motor offers simplified control for reversing. This is especially beneficial in regenerative drives. Compound motors have a field connected in series with the armature and a separately excited shunt field. The series provides fields for better starting torque, and the shunt field provides better speed regulation. However, the series field can cause control problems in variable speed drive application and is generally not used in 4-quadrant drives. This figure represents the system model of a DC motor. For the input, we have the electrical components such as voltage and current, and for the output, we have the mechanical applications such as angular position, angular velocity, rotor inertia, and friction. Our main input variable is voltage, and for output it is angular velocity. Below are the system parameters that will be used to generate a transfer function. This figure represents the transfer function developed using the system parameters that was found in the motor specification sheet. The transfer function describes various properties of the system, such as frequency response and the stability of a system. For this control system design, we would like to meet an overshoot of less than 5%, settling time less than 0.4 seconds, and zero steady state error. This figure shows the uplink response for the transfer function. On the figure, you can see the settling time, it was 1.81 seconds, which is a little too high. We want it to be less than 0.4 seconds. And also on the graph, you can see that it developed some steady state error. The root locus editor was used to develop the closed loop response. After making the changes, we developed an overshoot of 4.98%, and then also for the settling time, it was 0.00134 seconds. To meet the design criteria of less than 5% overshoot, less than 0.4 of settling time, and no steady state error, I needed to find the pole value, and so I used MATLAB to generate the poles of the transfer function. I used that value in the compensator editor. This figure showed the step response for a PID controller. I obtained a settling time of 0.005 seconds, an overshoot of 0.281%, and no steady state error. This project was designed to show that the PID function uses system feedback to continuously control a dynamic process. The purpose of the PID control was to keep a process running as close as possible to a desired set point, and we met the desired criteria for this project. Below is a list of references that were used in my project. Thank you for listening and watching my PowerPoint. Bye!